If chlorine had no preference for hydrogens, if it treated all of these hydrogens in the exact same fashion, what would be the predicted ratio of our primary product to our secondary product? What I mean by this is if chlorine had no preference for this hydrogen versus this one or this one, what would the statistical outcome be for primary versus secondary? Let's do this. Let's redraw it. How many primary hydrogens are there? How many primary hydrogens are there? How many hydrogens are attached to primary carbons? Well, it's really simple. It's 6. Okay. How many hydrogens are attached to secondary carbons? 2. This is secondary. So the ratio of primary to secondary is 3 to 1. There's 3 times as many primary hydrogens as there are secondary hydrogens. If chlorine has no energetic preference, just picks them up randomly, it would follow this predicted ratio. There's 3 times as many of these guys as these ones. And if they're all the same, then our predicted ratio here should be something like 3 to 1, or 75% to 25%. Something funny happened when people did this reaction for the first time. That's exactly what they predicted. Instead, the outcome of this reaction was roughly 50% primary product, where chlorine's attached to a primary carbon, coming from a primary hydrogen, and 50% of the time it was at the secondary position. This is an interesting result. If chlorine had no preference, we would predict 75% to 25% product distribution of primary to secondary products. When the reaction is actually done, we saw something different. In reality, we saw a 50% to 50% yield. And what this is telling us is, therefore, chlorine has some kind of energetic preference. This is a hypothesis. First hypothesis was we should see 3 to 1, 75-25. The experiment happened, and we actually see much more of the secondary product than we expected, and less of the primary product that we expected. And the subsequent hypothesis was that chlorine has some sort of energetic preference for secondary positions. That's the only way that we could explain this result. That somehow chlorine is going after these hydrogens at the secondary position at a much higher rate or with much higher frequency than these much more abundant primary hydrogens. And this subsequently led to the discovery and understanding that there's a difference in radical stability and there's a difference in breaking particular bonds. We're going to draw propane again. And this energy discussion is really useful right on the backs of our delta G discussion yesterday about acids. The bond association energy for propane at this primary position is equal to 98 kcals per mole. And this would be if we were to homolytically cleave this bond. If we were to chop this bond in half, the amount of energy to do so is 98 kcals per mole. The bond association energy at the secondary position in the same molecule is 95 kcals per mole. And it's slightly easier to break the secondary carbon-hydrogen bond, or a carbon-hydrogen bond at a secondary carbon. And the result, actually, the reason this happens is because the secondary radical is more stable than the primary radical. This is a secondary radical, this is a primary radical, and it's easier to make this one for reasons unbeknownst to us so far. I don't think we'll get to it today. Maybe we will. We have a few minutes left. But it's this particular species and this one are both highly reactive. They want electrons. But this one was actually a little bit easier to make by about 3 kcals per mole. And the reason it's easier to break this bond is because the stability of the resulting product is lower in energy or more stable than this one. If you think of those energy gaps we had, this secondary one is a little bit smaller. So going from here to here is easier. And the only reason it's easier is because somehow, almost magically, that this is more stable. So we're going to sum up that radical stability, or we could also say ease of radical formation, follows a certain trend, and that trend is that tertiary radicals are more stable than secondary, that's more stable than primary, and that's more stable than methyl. Here's a generic tertiary radical. The radical center is at a tertiary carbon. A secondary, well, that carbon will have 2 carbons attached to it and 1 hydrogen. This would be a secondary radical. That's more stable than a primary radical. Primary radical would have 1 carbon attached to it, and a methyl radical has no carbons attached to it. So this is the radical stability trend. And the way that it looks like, the more substituted the radical, the more stable it is. And if it's more stable, then it's easier to form it, as this previous discussion on this sheet of paper illustrated. So it's much easier to make tertiary radicals. They're more stable. Easier to make, more stable. This one, less so, but more than this one, and so on. The reason for this particular trend, we'll wrap this up in the last 3 minutes, then we'll take a 10-minute break. I'll catch my breath and prepare for office hours. Is that if we think about a radical, let's just actually compare two. Let's take a secondary radical and a primary radical. I'm telling you right now that this one is more stable. But why? Or if there's a hydrogen bond, carbon-hydrogen bond here, it's easier to pluck that off than if there was one here. And why is that? Well, we know that this species here is violating octet rule. It wants an electron, or it wants electron density. This is the reason why this is so reactive and unstable. We have this electron. This carbon really wants 2 electrons, or wants to satisfy the octet rule, and it can't. So this is deficient in electrons. This is deficient in electrons. Which one of these two has more stabilizing events for a center that's deficient in electrons? Think about the electron donating group effect of an alkyl group. We talked about acids yesterday. For acids, their conjugate bases are negatively charged, and if we had an electron donating group, it destabilized it. Here we have a radical. It's electron deficient. It wants an electron. And the result is that this alkyl group here, there's 2 of them, slightly stabilizes this radical. by donating electron density to it. The phenomenon this happens through is called hyperconjugation. We're not going to talk about that. It's a mouthful for a Wednesday morning or a Thursday morning, so we won't talk about it. But a primary radical only has one of these stabilizing events. There's this alkyl group has the ability to donate a little bit of electron density. Hydrogen doesn't. Hydrogen doesn't have any extra electrons to carry out this phenomenon, but carbon does. And so these radicals have different levels of stability based on different degrees of substitution. This is all we need to go through for today. This is actually quite a bit. We will have office hours again in about 10 minutes. All right, so